Welcome to our journey into complex analysis. Today, we are going to explore functions of a complex variable. If you have only ever worked with regular real numbers, you are in for a treat. We are about to upgrade our mathematical machinery from a simple one-dimensional number line to a rich two-dimensional landscape. This single leap will unlock powerful ways to understand everything from fluid flow to electrical circuits. Let us dive in and see how it works. To understand what a complex function is, think of a regular mathematical function, like a simple factory machine. You put in a single number, like 3, and it spits out a 9. That is a one-dimensional process, like walking back and forth on a straight line. Now imagine a much more advanced machine. Instead of taking a number from a single line, it takes a GPS coordinate from a flat map, a point with both a horizontal and a vertical position. When you feed this map coordinate into the machine, it processes it and spits out a completely new coordinate on a different map. This is exactly what a function of a complex variable does. Now that we understand the idea of mapping coordinates, let us look at the mathematical notation. In mathematics, a complex variable is typically written using the symbol z. This variable is made up of two distinct parts. The symbol x represents the real part, which corresponds to the horizontal position on a graph. The symbol y represents the imaginary part, which corresponds to the vertical position. Finally, the symbol I is the imaginary unit, which mathematically distinguishes the vertical axis from the horizontal axis. If x increases, you move right. If y increases, you move up. Together, they pinpoint an exact location on a two-dimensional plane. This brings us to the function itself. When we apply a mathematical rule, denoted by f, to our input z, we get a new output called w. Because the output is also a complex number, it must have its own real and imaginary parts. We call the real part of the output u and the imaginary part v. Notice that both u and v depend entirely on the original input values x and y. The term u is a standard real number formula that calculates the new horizontal position. The term v calculates the new vertical position. By breaking the function into these two pieces, we can analyze complex two-dimensional movements using basic algebra. Before we move on, let us see this with a concrete visual. The diagram you are looking at explains how a complex function operates as a mapping. Instead of drawing a single graph with an input axis and an output axis, we must draw two separate planes. On the left, we have the z-plane, representing our input space with x and y axes. On the right, we have the w-plane, representing our output space with u and v axes. The curved arrow shows the function picking up a point from the first plane and dropping it into a new location on the second plane. This visual approach is crucial because a four-dimensional graph would be required to plot this normally, which is impossible for humans to visualize. Now that we have a visual understanding, let us work through a concrete example. We are given the complex function f of z equals z squared. Our goal is to find the explicit formulas for its real part, u, and its imaginary part, v. Finding these parts allows us to see exactly how the horizontal and vertical coordinates are transformed by the squaring process. We start by substituting the standard definition of a complex variable x plus I times y into the given function. We place the entire expression for the complex number inside parentheses to prepare for standard algebraic expansion. Continuing with our calculation, we expand the expression using the standard algebraic rule for squaring a binomial. This rule states that the square of a sum is the first term squared plus twice the product of the two terms plus the second term squared. Carefully applying this rule to our real and imaginary components leaves us with three distinct terms. Next, we rearrange the terms slightly to make the imaginary unit more visible. We pull the symbol I to the front of the middle term for clarity, and we distribute the square to both the imaginary unit and the variable y in the final term. Now, we must remember a fundamental property of complex numbers regarding the squared imaginary unit. The fundamental definition of the imaginary unit is that it represents the square root of -1. Therefore, when we square the imaginary unit, the result is simply -1. This is a critical substitution in complex analysis because it allows us to convert an imaginary squared term back into a real number. By replacing the squared imaginary unit with -1, the final term changes its sign. The final term no longer contains an imaginary unit at all, becoming a purely real mathematical term. To finish this example, we group the terms that do not contain the imaginary unit together. We place these purely real terms inside their own set of parentheses, keeping the single term that still contains the imaginary unit separate. This perfectly matches the standard format of a complex number. We have now found our final answer. The real part of the output function, u, is x squared minus y squared. This tells us exactly how to calculate the new horizontal position. The imaginary part, v, is 2 times x times y, which gives the new vertical position. Together, these two formulas give us the exact location of the transformed point. Let us look at another example to see how this works with actual numbers. We are given a simple linear complex function defined as f of z equals 2z plus 3i. We need to evaluate this function at a specific input point located at z equals 1 plus 2i. This means we want to find out exactly where this specific point moves after passing through the function. We begin by plugging the given numerical value of the complex point directly into the function, wherever the variable appears. We place this entire complex number inside parentheses to ensure we multiply correctly. Continuing with our calculation, we distribute the constant multiplier of 2 across the terms inside the parentheses. Multiplying the real part by 2 gives us 2. Multiplying the imaginary part by 2 gives us 4 attached to the imaginary unit. The extra imaginary constant at the end is simply brought down. Finally, we combine the like terms together. The real number 2 stands alone. We add the two imaginary terms together to get a total of 7 attached to the imaginary unit. This final complex number is the exact location of our output point. Physically, this means our function took the original input point, stretched it outward, and shifted it upward. You might be wondering, why do we care about functions of a complex variable? In the real world, many physical systems involve two related quantities that change together simultaneously. For example, in fluid dynamics, water flowing through a pipe has both a speed and a specific direction at every single point. In electrical engineering, alternating current circuits have both a voltage magnitude and a phase angle that must be tracked. By treating these pairs of numbers as a single complex variable, engineers can use complex functions to solve incredibly difficult two-dimensional problems with simple one-dimensional algebra. Without these functions, designing airplane wings or analyzing power grids would require pages of messy, error-prone calculations. Let us summarize what we have learned today. A function of a complex variable is simply a mathematical rule that transforms one two-dimensional point into another two-dimensional point. It takes an input with a real and imaginary part, processes it, and produces an output that also has a real and imaginary part. By breaking the function down into these two separate real number formulas, we can easily track how the horizontal and vertical positions change. This powerful tool forms the foundation for analyzing complex systems in physics and engineering. You have now taken your first major step into complex analysis. Great job!